Today, we're going to start or continue where we had left off talking about chapter 15. So in 15.2, we're going to talk about exponential and logistic models. One of the most common situations to describe with a logistic or exponential model is population. And that can actually be generalized to talk about things other than just populations, but let's start with population. So the general or the exponential population model is here, where P of t is the population at some time t. And that's equal to P naught, which is the initial population, times the quantity 1 plus R over 100, where R is the rate of population change as a percentage, and then T is some time. Keep in mind here that this is still like a y equals ax or a times b to the x situation, where just this 1 plus r over 100 is the b value. So the same rules that we had about whether things were growth or decay are still dictated here. Since this is 1 plus r over 100, if we're talking about a decay, what do we have to have for r? Yeah, it has to be a negative value. Very good. So just a quick little example. So we have a couple of population models here, and we're asked first whether they're growth or decay. So if I look at this first one, 12,587 times 1.0384 to the t, is that growth or decay? Growth. How do you know? Yeah, good. So that's bigger than 1, so that one's growth. And then likewise, this one would be decay, right? Now, the question also asks to find the constant rate of growth or decay. So what we're going to do is we're just going to take that value for b and set it equal to 1 plus r over 100. And then we can just solve this equation for r. So what do we end up with? I subtract 1 and then multiply by 100. And we get that r is 3.84%. Right? No big deal there. If I do the other one, we'd have 0.9867 equal to 1 plus r over 100. If I do the same thing, what do you notice is going to happen when I subtract 1? It's going to be a negative number, right? So with these decays, we can describe the R two-way. You can say in part B, the rate of growth is negative 1.33%. Or you could say the rate of decay is just 1.33%. So that word decay can be used in substitution of the negative sign. Just kind of keeping that in mind, just as a little vocabulary. Again, if you're doing a story problem, those little like vocabulary details can be kind of important. Not difficult, but you have to kind of remember. Let's do an example where we have a story problem, or at least just a situation in words. And here we're just being asked to write the population model for this. So since it's talking about population in the problem, we know we're going to be using our population model. And because it asks to write a model, I know that I'm going to have my independent and dependent variables still in the equation when I'm done, right? So my goal is really just to fill in the value for P naught and R, right? So P naught is the initial amount. In the problem, it says that we're asked to determine the population model with the initial value of 15. Well, okay, that's pretty easy. And then the R, it says increasing at a constant rate of 6%. So R is just going to be positive 6. And then with the T, I guess before we write that, we should determine what unit we want our T to be in. Because in the problem, or in the description, T is just general time. But there's lots of units we could represent our time in. What would be the obvious choice for our T here? Years, yeah. So if we're choosing years, it's just T. And notice that I could simplify 1 plus 6 over 100. And typically when we write our models, you'd want to do that. So our population model is just P of T equals 15 times 1.06 to the T with T in years. That's good. Let's look at another example that's quite similar to this. So this one says, determine the population model with initial value of 15, increasing at a constant rate of 6% every 6 months. So this reads almost identical to the previous example, right? What's the only difference? Yeah, the first one was a year, this one is 6 months. So this part is all going to be the same, right? Everybody's cool with that? Now we just need to pick what unit we'd like to represent the T in. There's probably 2 obvious choices here. Months, okay. So if we do months first, what I need to then think about then is how much of a compounding period happens inside of 1 month. 1/6 of it, right? If it takes 6 months to get a compound and we're doing 1 month, that's going to be 1/6 of a compound, right? So instead of writing T, I'm going to write T over 6. Everybody's okay with that? Now, if I had done this, the other suggestion I heard was that to do T in years. If we did that, what would I write as the exponent? Not T over 2. 2T. Because how many compounding periods do we get inside of a year? 2, right? 6 months happens 2 times inside of a year. Or there's even a third way that would be not unreasonable. You could just write it to the T where T is, 6 months, right? Or 6 month groupings. Now that's a little like messy if you want to analyze your answer. But if your data set is just like, yeah, every 6 months I have to do this, then there's nothing wrong with doing it that way. Or the situation just calls for a population estimate every 6 months. Continue going here. Suppose that a colony of 120 bacteria is put into a petri dish and the culture doubles every 3 hours. Predict how long it would take for there to be 400,000 bacteria. So when I read this, I really read this as like a two-step situation. The first step would be to write some model. I'll call that model P of t. And then step 2 would be to solve the equation P of t equal to 400,000. Everybody's okay with that idea, or how I got that from the words that were written down? Okay. For step 1, we'll start by writing our model. So again, we know this is a population model, so we'll start with the initial amount, which is 120, good, plus times 1 plus r over 100. What is the r in this situation? Because I don't see a percentage anywhere in here. So what word in here is indicating our r? Doubles, great. So you say that in that case, r should be 200?
No, it should be 100.
Should be 100, very good. How'd you come up with that?
Well, 100 and then plus 1 is 2.
Yeah, if I did 1 plus 100 over 100, that is 2. That would be our doubling effect, so that works. Great. And we should pick a unit for a unit of time. What seems like an obvious unit for our t?
3 hours.
Yeah, I would do it in hours also. It wouldn't be, you could still do it in 3-hour blocks. That would be okay. If I do t in hours, how would I write the exponent though? T over 3. Okay. And again, we could simplify this down to just that, right? In step 2, we're then going to solve this equation, right? And there's 2 ways we've talked about how to do this. Last time we just used the graphing calculator to graph these and find the intersection. Let's do that again here. But after we do that, we'll also kind of show you what it looks like algebraically. So if I'm going to do this graphically, I'm just going to do the left-hand side of my equation into y1. And the right-hand side of my equation into y2. Everybody's good with that? Okay. I'm going to set a window now. So, okay, this is doubling. I don't want to count the doubling to 400,000 because it feels like it's going to be a lot of doublings. Maybe we'll just go up to like 100. That probably is sufficient. Doubling's pretty fast. And then the y-min, well, the minimum is going to be starting at 120, and I need to go north of 400,000. So I'll probably do 0 to 500,000, just so everything is kind of like a nice round number. Okay, that looks good. Let's hit graph. So here coming in should be my, oh, what happened here? Oh, Mr. Kulak, why did I write a half instead of 2? I don't know. There's my population curve. Woof, that got Steve. Steep, not Steve. How to get Steve? I don't know. That's weird. But the point is I can see the intersection. That's all I really care about. So I do second trace, intersect command, and since there's only 2 curves, I just press enter 3 times. And I get about 35.11. Now, if I wanted to solve this algebraically, what are we going to have to use to do this? A logarithm. Very good. Now, we haven't talked about logs yet, so if you don't feel comfortable doing that, continue graphing. That's fine. But I know that we've talked about this last year, so why be coy about it? We know these things exist. We should remember, hopefully, how to kind of use them with a little refresher. Let's start that refresher today. So if I want to solve this equation, what's the first thing that I'd want to do? Not yet. So I want to follow the reverse order of operations.
Divide by 120.
Yeah, so the first thing I would want to do is divide by 120. Yep, because we have to get the exponential piece by itself. Exactly right. And obviously, 400,000 divides by 120. That simplifies that fraction. I don't really care. Eventually, this is all going in my calculator. I'm going to just spare myself the possibility of making a big oopsie, reducing fractions right after lunch when I am ready for a nap. So now, Elaine, I think it's time to do the log. Which logarithm would you like to use? There's logs of lots of different bases. What base would be most appropriate for this situation? You can use that, but it gets a little messy. There's a better choice here. I would choose the base of my logarithm to match the base of my exponential. So in this case, I'd pick log base 2. So I would do that to both sides. If you do a log of a different base, the simplifying becomes quite a bit messier. If you choose your log base to match your exponential base, everything works out pretty nice because you have like a 1-to-1 cancellation. That would be my suggestion. But to be clear, you could use log base 10. That would be okay. This is just streamlines it a little bit. And my life is complicated enough. I'd like to make good choices and keep things less complicated. The last step then will just be to multiply both sides by 3. And I'm going to write that 3 out front, just so I'm not confused about whether the 3 is inside the log or outside the log. Just like when I deal with radicals, I try to put all the stuff that I do to the radical in front of it so I don't get confused about whether is that times 3 under the radical or outside of the radical. The same thing is here with the logs. I want to try to make sure that I have that really clear to myself. So I'll do 3 times. And then to do log with a different base on it, I can press the math button and then scroll down to the very bottom till I find that log base command. And that lets me write in any base that I want. So in this case, we're writing in 2. Then we'll type in our 400,000 over 120, press enter, and we get that same 35.11 number that we saw before. We okay there? Now, Nolan had suggested when we're writing our model, what if we just used t in like 3-hour increments, right? And we could certainly do that. If we did, I would just delete out the times 3, or divides by 3, excuse me. If I hit graph now, notice that's a heck of a lot steeper. Well, it just kind of shifted, but that's fine. If I do trace and then intersect, here I get 11.7. So let's write down a little bit of what we've done so far. I forgot the last decimal there. What was that? 0, okay. But what is this T? Yeah, that's 3-hour increments. Now, what does that mean? If I do 11.7 times 3, that's going to give us that same 35.1 hours that we saw before. So if you choose to use your T in kind of a non-standard time period, keep in mind that you'll probably have to do a little bit of multiplication with your answer at the end to get into a standard unit. In particular, if the question asks for time in hours, which would be what I would do on a test or whatever, I would tell you the unit that I want my final answer in, just so I don't have to go and check and be like, oh, why did this person do this problem in years? 0.046, like how many hours is that? You know, like I don't have to do a million conversions to check all the possible answers. I'm just gonna be like, use this unit, and then, you know what I mean? So that's that. We've seen how to do that a couple of different ways now. Another application where we can use this population model that isn't exactly having to do with population is with radioactive decay. So radioactive decay is like a chemistry idea. So in chemistry, you have elements, right? And an element is defined by the number of protons it has, right? And for a given element, you can have lots of different versions of that element. Those are called isotopes, depending on how many neutrons you also have packed in your nucleus. And depending on how many neutrons are in there, your element may or may not be very stable. If your element is not very stable, it's going to emit some kind of radiation. It's going to emit some of these atomic particles to try to move to a more stable configuration. In some types or some situations, that means that one element is going to give off neutrons and protons and become a new, completely different element, right? That process of releasing atomic particles and reaching a more stable configuration is called radioactive decay. Typically, we measure radioactive decay by the half-life of the substance. The half-life is the amount of time it takes for half of the original material to decay into, its more stable configuration. So for some elements, that's really, really fast, especially like the synthetic ones. Might be a matter of seconds or even less than seconds. Some of them, it's very, very long. It could be thousands of years for a half-life. It just kind of depends on the specific isotope you're talking about. Does that enough context for you guys to understand kind of what we're talking about here? Okay. Let's grab an example and show you how we should do one more thing before this. The big takeaway, though, the thing that we want to remember for our population model is when we see half-life, that would just mean that R is negative 50%. That's the thing that we That's kind of the key that we need to be using the population model that we just described before, is that R is negative 50%. Whenever we hear half-life, right? We know it's negative because of the word decay. It's radioactive decay, so there's a negative sign. And half is 50%, right? If something's on sale for half off, it's 50% off. Okay, sorry. Now we'll look at the example. All right. So it says that suppose the half-life of a certain radioactive substance is 35 days, and you have 10 grams of the substance initially. Find the time it would take for there to be 1 gram remaining. So again, this is a two-step problem, right? Step one, we're going to write the model. Step two, we'll solve that model equal to 1 gram. So the initial amount, well, that's just going to be 10 because it says we have 10 grams of the substance initially. And because we're talking about radioactive decay and half-lives, I know R is negative 50. And then what unit are we going to, of time, should we use it for our T? Okay, that's what I would use. If that's the case, what should the exponent be? Well, T over 35, yes. Because 1 day is 1/35 of our half-life, right? If a half-life takes 35 days, 1 day is 1/35 of it. Okay? So that's step one. Step two, then, we're just going to take that and set it equal to 1 and solve. We've done this with a logarithm now. I'm just going to do this piece on the calculator kind of from here on out until I run into something that's decidedly different. So let's see here. I have 10 times 0.5 to the x divided by 35, and then 1. Okay. I'm going to set my window now. So I'm going to think about this. The x's are often the trickier one. Obviously, since t is time, the x-min should be 0. But let's think about this. So to go from 10 grams, if I do 1 half-life, that turns to 5. 2 half-lives is 2.5. 3 half-lives gives me 1.5. 4 half-lives will be less than 1. So I'm going to pick my x to be at least 4 half-lives. So if there's 35 days to a half-life, I'd want at least 140 for my x max. I'm going to do 150 just because it's kind of a nice round number. And then we'll scale by 25s or something. And then the min for a decay is always going to be 0. You can't get less than 0 of something. And the most we'll ever have is at the beginning, since we're decaying, so that should just be 10. And that should do it. Let's hit graph and take a look here. There's my radioactive decay model. There's 1 gram. Second trace, intersect command, enter, enter, enter. And we get 116.3 days thereabout. No big deal, right? And we talked about this again last time, but when we talk about population, an exponential model really might not be the best model over the long term to describe a population, right? You can get some wacky, kooky answers that don't seem very plausible, where the population is like, oh, I had 3 bunnies, and then 100 years later, I have 10,000 bunnies. That seems unlikely. Because we know in like the real world, like you run out of resources, or you run out of space, or like you have such a high population of bunnies that they're now really prone to get eaten by other predators because they're all over the place and they're really easy to find, or diseases come in because the population density gets really high, or any number of things will kind of go to tamp down that population growth. So what turns out to maybe be a better model over the long term is a logistic model. And we talked about the logistics last time, but let's look at an example of a population model given with a logistic function. And we'll remind ourselves a little bit about these logistics as we answer this guy. So this one says you start a bunny petting zoo. You determine that the population of bunnies on your farm can be modeled by the equation B of t equals 800 all over 1 plus 99 e to the negative 0.5 t, where t is measured in years. Okay, so we're given our logistic model there. And then it says, how many bunnies do you have initially? Well, what value of t does initially mean? 0. So we really just want to do b of 0 to answer this question. So negative 0.5 times 0 is 0. E to the 0 is 1. 99 times 1 is 99. 1 plus 99 is 100. So this is just 800 over 100. Or just 8 cute, fuzzy bunnies. Everybody cool with what we did there? Remember that anything non-zero to the 0 is 1. What's 0 to the 0?
Oh, it's like the weird thing, like undefined.
It's not undefined, isn't the word that we want. Indeterminate was the term for that. Yes, good. B says, what is the maximum sustainable population of bunnies on your farm? So here's where I need to remember what we talked about from logistics previously. So one of the features of a logistic function is that you have two horizontal asymptotes. One of them at y equals 0, and the other at y equals c, where c is the numerator of our logistic model. So that y equals c is going to be the upper bound for our function. That would be like the maximum population that our function can have. So that's going to be our maximum sustainable population for bunnies. So I did that using no calculation, just knowing what I know about logistics. Say, okay, what's the upper bound for that logistic going to be? It's going to be one of the horizontal asymptotes. One of them is 0, the other is 800. Obviously, 800 is the one that I want there. Part C says, how long will it take for you to have 500 bunnies? Oh, that's a B. So I'm just going to solve this. So let's do this on the calculator, and then we'll take a pause and do it by hand algebraically also. Sound okay with you guys? Since this is a different looking function, although it's going to not be demonstrably different solving. So here, if I'm typing this into my calculator, I'm definitely using that fraction command because this is going to be kind of a parenthesis nightmare getting that to do what I want it to do without, or just in one line. But if you do alpha y equals and pick that first fraction option, numerator over denominator, that makes life pretty easy to type in. Everybody's okay with what I did there? Okay. This is years. We're starting with 8 bunnies. What do we know about the way bunnies reproduce? Fast is the point, yeah. So I don't know how long this is going to take. Maybe I'll take a guess and say like by 50 years, I hope to have it. If I'm wrong, I can always go back and make that bigger, but I'm just kind of taking a guess here. But 50 years seems like a long time. Now I know that for my logistic function, the lower bound is the horizontal asymptote, so y equals 0, and the upper bound should be the other horizontal asymptote, y equals 800. So I'll just use those as my y mix and y min and y max, which is nice that I don't really have to think about those when I'm doing a logistic. I know I can see the whole thing up and down. And I think I overshot the length there a little bit because, you know, after 20 or so, I'm just sitting here at the horizontal asymptote, but that's fine. There's my intersection. So second trace, intersect command, enter, enter, enter. And I get about 10.21 years. And now let's also do this one algebraically just to kind of, well, get some extra practice. Okay, so what would I want to do here first? Yeah, so I want to get that variable out of the denominator. So whether you think about that as multiplying both sides by 1 plus e to the negative 0.5t or doing cross multiplying or whatever, that's fine. Either way of thinking about it is okay. I'm going to think about it like a cross multiplication problem, but what Joe said was exactly the same thing. So that gives us this. Divide by the 500. Now I'm going to reduce that fraction because, well, quite frankly, it's like an easy fraction to reduce because 800 divided by 500, just 8 over 5. But if you didn't want to, that's fine. If you don't want to risk it, it's all going in your calculator eventually, so you can hang on to the whole thing if you want. Not a big deal. What next? Subtract the 1. Again, you can write minus 1 next to this fraction, or in my case, I'm just going to subtract 1 from that fraction because it's easy to math for me to do in my head. But if, again, you don't feel confident with it, don't risk it. Just write it next to it and just type it all in the calculator. Now we got to get rid of that exponent base e. What do we use to do that? A logarithm, specifically the natural logarithm, I heard somebody say. Remember that the natural log, ln, is just log base e. So we'll do the natural log to both sides. And log base e cancels out exponent base e, leaving me with just the exponent. So my last step would just be to divide by negative 0.5, or really what I'm going to think about it is multiplying by negative 2. So that's what I'm going to be typing into my calculator. Wait a minute, what happened here? Why am I like a order of magnitude off? What did we do? That, okay. That is that, okay. We did that. Did that. Oh my gosh, guys.
What?
Mr. Kulik, you're so dumb. I forgot the 99 there.
Yeah.
Okay. There we go. There it is. Mr. Kulik, you're so silly. That makes me feel better. That's such a Mr. Kulik mistake where you forget to write something down the right way. All right. Moving on to the next piece. We're going to start the next section today also. And here we're going to formally introduce logarithms. Does anybody remember the formal definition of a logarithm that you would have gotten way back in your Algebra 2 class?
Zero versus exponent. Right?
Yeah, so that's the idea. So the definition is just that the logarithmic equation b to the y equals x is equivalent to the logarithmic equation log base b of x equal to y. So that is our formal definition of a logarithm. It's essentially just the inverse operation of an exponential. So, oh boy, hang on to those papes. Let's do a couple of numeric examples just to kind of review how to use this definition. So the way I'm going to do this is I'm going to start by just saying, okay, log base 4 of 16 is equal to a. So if I use the definition of a logarithm, I can say 4 to the a is equal to 16. And I recognize 16 is just 4 squared. So clearly a just has to be 2. If the bases are the same, then the exponents have to be the same. Is that okay with everybody? The next one will say, okay, that's equal to b. So I can say 5 to the b is equal to the square root of 5. And then how do I write the square root of 5 as a base 5 number? It's not negative 2. It's 1/2. Yeah. So remember that, like, that's the rule for radicals. So again, we can see that b is just clearly 1/2. So this next one we'll call c. This one's a little bit tougher. What do we have? We have 3 to the c equals 1 over 27. So writing 1 over 27 as a base 3 number is kind of tough to do in one shot. What I would do first is I would recognize that a negative 1 exponent just makes a reciprocal. So 1 over 27 is just 27 to the negative 1. And then I go, hey, 27, that I recognize as 3 cubed. So 27 to the negative 1 would be 3 cubed to the negative 1. And how do I simplify an exponent of an exponent? They multiply. Very good. So that gives me 3 to the negative 3. And that then tells me c is negative 3. Is that okay with everybody? Just kind of reviewing some of these exponent rules as we go. So d here, let's see, we have 12 to the d is equal to 1. How do I rewrite 1 as a base 12 number?
0.
Yeah, 12 to the 0. So there, d is equal to 0. Again, any non-zero number to the 0 power is 1, so that's nice. And then the last one, we'll just say that's equal to e. So here I have 8 to the e is equal to 8. Well, Mr. Kulik, e is just 1. Everybody's kind of remember that stuff from last year, doing this. So some takeaways here. Any log of 1 is going to be 0. Log base b of b is going to be 1. log base b of c is less than 0 if c is less than 1. Log base b of c is going to be greater than 0 if c is greater than 1. Everybody cool with that as our takeaways? Okay. That kind of covers all the possibilities there. Just a little bit of vocab review. I think we've used both these terms so far, but let's write them down anyways, just in case some of us that have been following along aren't as familiar, don't have as good of a logarithm memory as some of us others did. There's two logarithms that get a special name. There's the common logarithm that we abbreviate just log with no subscript. That we understand as log base 10. And then there's the natural logarithm that we abbreviate with the ln, who has a base of e. Nothing more to it than that. I just needed to write them down and say what the definitions were again. So let's do a couple of just simplifying examples. We're going to try to do these without having to write anything down. I'll talk about how we get them in a second, or as we write them down. But what's our answer for A going to be? 3. Good. So you should think about that as log, and then 1,000 is 10 to the third. So log base 10 cancels with exponent base 10, and we're just left with 3. Okay. How about B? What should that one be? Good. 1/5 or 1/5. Good. Because the fifth root of 10 is just exponent 1/5. How about C? Keep in mind, 0.01 is 1/100. -2. Yes, very good. How about D? What's that going to be? 5. Very good. Exponent base E cancels with log base E. We just have 5. How about E? We're going to use exponent base 10 to cancel the log base 10. So x is 10 squared, or 100. And then F should be E is our exponent base that we use, so we end up with e to the 5th. Oops. Y equals e to the 5th. Is that okay with everybody? Okay. Again, if I'm doing any of this too fast or you don't like what happened, holler at me and we can repeat or slow down or show some more detail. But this is stuff at our level that the expectation of being able to do some of this in our head is not unrealistic. Again, we'd like to get fast at doing this stuff so it doesn't take a bunch of time and we can feel comfortable zooming through some stuff, because this should be really the second time you've seen this material. Now, that doesn't mean it has to be perfect, right? But if I'm going too fast, you have to let me know. There are 4 big properties of logarithms. In all reality, only the first 3 are going to be ones that we'll regularly use, the product, quotient, and power rules. The last one, the change of base formula, when Mr. Kulik was a high school student, would have used the heck out of. You guys no longer really need to use this. The reason is you have a calculator that can do the log of any base. When Mr. Kulik was in high school, he did not. When he started high school, didn't have even like scientific calculators existed, but weren't super duper common. So you didn't even have a log button on your calculator. So to do some of this stuff, you'd like, if I want to do like log base 3 of 5, I'd go to the back of the textbook and find the table of logarithms. I'd look up the decimal value for log 5 and log 3, and then divide those on my 4-function calculator, which sounds like a nightmare, and it kind of was. By the end of high school, it was getting to be pretty common to have a scientific calculator that either had the common log or the natural log, or maybe both, as a function built into it. But even then, still, we didn't have the log of any base option. I think some of your scientific calculators now have that. That was not a thing, or very common option when I was in high school. So again, still, we're using using the change of base formula. We got away from having to look the number up off a table, which was lovely. That was really exciting when we didn't have to look up the numbers from the table. But you still use the change of base formula, almost any log that you did. Now, it's not hugely important for you guys because your calculators can do the log of any base really easily. But that's my little spiel. I think we're gonna prove these guys in the problem set, but let's do the first one together and kind of talk about what the process is going to be. Oh boy, that's not at all where I expected that to land. So here we're going to prove the product property for logarithms. That is that log base b of rs is equal to log base b of r plus log base b of s. So what I'm going to do is I'm going to start by taking the log base b of r, and setting that equal to x, and I'm going to take log base b of s and set it equal to y. Then I'm just going to use the definition of a logarithm to rewrite that as b to the x is equal to r, and then b to the y is equal to s. Everybody's good there? I'm then going to just multiply these two equations together. So I get the left-hand sides multiplied together equal the right-hand sides multiplied together. Everybody's still good? When I multiply b to the x times b to the y, how do I simplify that? B to the x plus y, right? Everybody's good? Now I'm going to take the log base b of both sides. Now log base b cancels with exponent base b. And x, remember, that was just log base b of r. And y was just log base b of s. And now I have exactly what I was looking for. So where was the critical step here? It was using that property of exponents to rewrite the product of two exponentials as the sum of their exponents. So the idea here was I rewrote these logarithms as logarithmic equations, translated them into an exponential equation, multiplied or divided or did whatever I needed to do, and then took the log of both sides, or used the property of exponentials that I needed to simplify, took the log of both sides, and then I just basically substituted back and had my answer. The proofs for the other ones are going to be quite similar to this in technique. So when it comes time to, you see those in the homework, the pattern is very much similar. Now, these properties, the product quotient and power property, are going to be used pretty routinely to do two kinds of problems dealing with logs. The first kind that we'll talk about is expanding. In an expanding problem, you want to take a single logarithm and write it as the sum or difference of many logarithms. So you just want to break it up into as many logs as possible. When we do that, the order that we use our properties is typically going to be quotient, product, and then power. I say typically because you could always have like a parenthesis involved somewhere where it's implying that like, oh, you should be doing this exponent before you do something else, in which case you'd want to do the power property before. You know, if you had like parenthesis around a fraction, you'd want to do the power property before you did the quotient. But in general, this is what you'd want to do, or the order that we'd want to do things. So let's grab a couple of examples and work through these. And I think that's where we stopped in fifth hour. So that's where I'd probably want to stop today, is after these examples. So if I look at A, the first thing I do is I want to look for a quotient property. If I go and I look at the 4x, is anything being divided? No, man. So no quotient property. Next thing I look for is a product property. Is anything being multiplied? Definitely. Where's the multiplication occurring? Between the 4 and the x, right? So if I apply the product property, I can say that's log base 3 of 4, and then plus log base 3 of x. Everybody's good with that? Now I need to take a look at my results, my log base 3 of 4 and my log base 3 of x, and I need to check quotient, product, and power property with each of those. So let's start with log base 3 of x. Is there a quotient property there? No. How about a product property? No. How about a power property? On the x? No, right? That's fine. If I look at log base 3 of 4, now I'm going to do the same thing. Is there a quotient property there? No. Is there a product property there? Okay. Is there a power property there? Well, you have to squint at it a little bit, but you could have said yes to either power property or product property, because 4 is not a prime number. So if I do a prime factorization of 4, I can either think of that as 2 times 2 and do a product property, or think about it as 2 squared and do a power property. Now, I would prefer doing the power property because it's less simplification later. But there is a power property going on there. So that allowed me to move the exponent to a coefficient. And then we said that there was nothing happened with the log base 3 of x. So that's just going to stay the same. And that's as far as I can go. Everybody's good with that? Okay. Okay. If I have log of 3ab to the 5th, again, first thing I look for inside my logarithm is a quotient. None of those. Next thing I do is I look for a product property. How many product properties do you see? How many multiplication symbols are there? 2. So there's 2 product properties. There's a multiplication between the 3 and the a, and between the a and the b. Well, b to the 5th, really. So when I do my product property, I can do both of them at the same time. That's fine. Now if I go and I look at quotients, log 3, log A, log B to the 5th, none of those are quotients. If I look at products, log 3, log A, log B to the 5th, neither of those are products. If I look at powers, log 3, log A, no powers there, but log B to the 5th has definitely got a power property there. So I'm going to move that exponent of 5 to a coefficient outside the logarithm, and that's good there. Everybody feels okay? All right. And then let's do the last one here. Okay, first thing we look for inside the logarithm is quotient property. I definitely see division going on there. So what we're going to do is we'll write that as log of the numerator minus log of the denominator. Everybody feel good? Okay. Obviously, each of those, none of them is a quotient property because none of them are fractions. So product properties next. If I look at log of 2x, that's a product property. Everybody feel good there? There's no product property with log of cube root x minus 5. Is there a power property for that? Yes. What is the power property? It is a 1/3. Good, because the cube root is the same as a 1/3 power. Now, obviously, log 2 and log x, there's nothing left to do with those, right? But let's look at that last one, log of x cubed minus 5. Is there anything more to do with that? So, well, this thing is never true. So you can't distribute a logarithm. So you can't separate them that way. I see an exponent here, though. Could I do another power rule here? What do you think?
Yeah.
You definitely can't. The reason is because that exponent isn't applied to everything inside the logarithm. If it was written as x minus 5 quantity cubed, you can power property that. But if it was like x cubed minus 5 cubed, no power property there. You could factor it as a difference of cubes and do a product property then. But with what we have written here, x cubed minus 5, there's nothing to do with that at all. Even though there is an exponent there, don't be fooled, because the exponent isn't around the entire argument inside that logarithm. Does that feel okay? You guys see the difference? Okay. So that's going to close what I wanted to do today. So at this point, you guys should be able to do gulp 17 to 82. Now that looks like a lot of numbers, and I agree that is a lot of numbers. Here's the deal, though. A bunch of these are like going to be 30-second or less problems. It's going to be like, use the change of base formula in your calculator to do log base 3 of 7. It's like, dude, all I have to do is type this in my calculator and press enter. Like, that's a 10-second problem. Or it'll be simplify without a calculator, log base 4 of 16. It's like, okay, well, this is, like we did those. It's like a 30-second problem for a lot of those. So half or more of this problem set right here is going to be stuff like that that's should be really, really quick. Okay? This expanding was probably the most time-consuming thing in this set, which is still not tremendously difficult or time-consuming to do, because it's not like a million trillion steps. You know what I'm saying? So it is a lot of problems, but most of them should be really quick. Okay? But this is where I'm stopping today. Everybody cool? Okay. Questions for me about anything before we pause? Okie dokes.